Welcome to our today's webinar. My name is Michael Schöneich. I'm an application scientist at Netsch Analyzing Testing, and today I want to present you our webinar about the areas of application for simultaneous thermal analysis with ceramic materials. So in the upcoming 20 to 30 minutes, I will present you an overview, a brief overview about simultaneous thermal analysis, what is or what type of methods we will use for this one, and how we can use this technique in the fields of ceramic materials in the ceramic processing chain. So we will see some analysis of raw material or product materials. We'll have examples for processing chain, like for instance a binder burnout process, and also some application examples for the pure materials at the end. Before we come to this application part, which is of course the main part, I will start with a short introduction about ceramic materials and the thermal analysis. So, as far as I imagine, the most of you are familiar with ceramic materials. Nevertheless, just a short summary of these kind of chemical components. They are one of the major material groups in solid-state science, and they are typically characterized by the point that they are inorganic materials, that they are mostly non-metallic. However, they comprising metal and non-metal atoms inside of their structure, which is based of ionic and covalent bondings. So we talk here about crystalline, semi-crystalline, but even about amorphous materials typically. The materials itself are normally formed out of a raw mixture by chemical or physical interactions. These physical interactions or chemical interactions are normally processing parameters like binder burnout process, reaction processes, or one of the interesting points, sintering processes, which allow, for instance, also to tune the properties of this material. If you look here at this short definition, you see that we are not defining a special chemical composition. This means ceramic materials are covering a wide field of different chemical compositions, which mean we can, for instance, talk about oxide materials, we can about nitrides, carbides, and whatever. And therefore, we have also a wide variety of possible physical properties which are available with these kind of materials. Typical properties would be a high temperature stability, a high hardness, in the same conduction with a low ductility, pure electric conductivity, and chemical resistance. Nevertheless, due to the field of wide variety of different chemical compositions, we have a highly possibility of exception of these typical properties. So there are also well-known ceramic materials for piezoelectric ceramics, like for instance barium titanide components, or even superconductive ceramics like the carburetes. Because of this wide variety of properties and composition, we normally classify the ceramics based on their application, which can start by traditional tableware, whiteware, up to refractories of cement, or in the nowadays also for more advanced ceramic applications, like in the electronic industries for electronic, magnetic, or optical ceramics, or advanced structural ceramics, like for instance in the nuclear plant construction or the automotive field. Beside this kind of classification, of course, we can also classify them by composition, but as mentioned before, there are in principle different groups, and therefore we can see here, for instance, groups of oxides, silicates, carbides, nitrides. So here each group has a subgroup built up, but in principle it is also possible to classify them by their composition. So far to ceramic materials in basic. Why we are talking about ceramic materials in combination today with thermal analysis? Because thermal analysis can provide a possibility to characterize these kind of materials, and especially if we talk about their high temperature application. In most cases, temperature is of course one of the main factors. If we look now in the methods of thermal analysis, which is just a broad overview here, then we have different techniques which are more or less suitable to analyze ceramics. And if you follow our webinar series already a little bit, then you have maybe heard the last two webinars. One was about dilatometers, which is here shortened by DIL. And in this webinar, it was the topic that we talked about the length change, which can be measured in correspondence to the temperature. Therefore, for instance, we could analyze shrinking processes during sintering and so on. The other webinar was covering, for instance, the LFA, the laser flash analysis, where we have faced with the heat conductivity or temperature conductivity of materials, which is one of the main thermophysical properties of ceramics. So if you're interested in these two webinars, you can check our homepage and also have a look on the recording of these webinars. Today, we will cover the simultaneous thermal analysis, which is nothing else than the combination of two techniques of thermal analysis at the same time. And typically, we talk here about the combination of thermogravimetric analysis, TGA, and differential scanning calorimetry, DSC, or difference temperature analysis, DTA, which is facing caloric effects of materials. So if you are maybe not familiar with these two techniques, please let me short explain them to you. First of all, thermogravimetric analysis. In thermogravimetric analysis, we are analyzing the mass of a substance, which is measured as function of temperature or time, while the substance is subjected to a controlled temperature program in the specific atmosphere. So if we take this standard here, we can build our own thermogravimetric analyzer quite easily. So we see we want to measure the mass of the substance. So what we need is a balance. This balance is just connected with a balance beam where we can place our sample because we want to analyze the sample. And as you see in the second part of this standard, we want to perform this with a controlled temperature program. So we'll take a furnace to heat it, the sample, cool the sample, or just hold it isothermal at higher temperatures, for instance, for tempering processes. So you see the building construction of such a thermal analyzer in general is quite easy. On the next slide, you see now one of our machines from NETCH, which is the STA 449F1 Jupiter. And this is one of these simultaneous thermal analysis instruments here shown in a schematic sketch. So what you see in principle, it's the same build-up like I showed before on the slide of the general thermogravimetric analyzer. So you have a balance system here in the bottom part. You have more or less the sample carrier or the balance beam here in the middle, and the sample would normally sit around here. And therefore, this all is surrounded by a furnace and can be heated. Of course, there are some more special parts like protective tubes to allow a specific atmosphere inside of this reaction room, but in principle, this is the same construction principle like I showed before in the general overview of the standard. So the next question is, what can we measure with TGA? So what are the information which can get out of this kind of thermal analyzing technique? This is, I think, the most interesting part. So we can analyze, of course, materials itself. So we can identify, characterize products by their mass change behavior. So we can see, for instance, do we have water releases? Do we have hydroxide decompositions? Do we have decarboxylation reactions? And so on. Furthermore, we see the decomposition temperatures directly from these analyzers. So we can see when these decomposition reactions occur. Of course, we can, at the same point when we see decomposition temperatures, we can also talk about thermal stability of materials. We can do composition analysis because we see all the different kind of components which are decomposing. And finally, we can also oxidize materials. So we can also introduce oxygen-containing atmosphere, even water-containing atmosphere, and then we can look at corrosion or oxidation processes. Furthermore, there is a possibility for advanced analysis, which are typically facing the part of kinetics. So we can also look at the time evolution of these kind of decomposition reactions. So far to the TGA. Let's head over to the second part of the simultaneous thermal analysis, the differential scanning calorimetry. Here we talk about a technique in which the heat flow difference between a substance and a reference material is measured as function of temperature, while the substance and reference materials is subjected to a controlled temperature program. So if we start again with this schematic screwing, we see here we have a temperature program. So we need first of all, again, a furnace. And inside of this furnace, we have now a sensor to measure more or less the temperature of a sample substance and the reference material. So we will just place a sample on one sensor side and the reference on the other sensor side. And what we are now doing is more or less already inside of the name of the scanning differential method. We try to make a difference analysis of the behavior of these two sample and reference positions. And this looks in principle like you see now on the next slide. So when we heat up the system, in principle the sample and the reference will firstly follow the temperature profile of the furnace, which you see here in the starting part. The reference itself is typically a material which not change over the entire temperature range which will be investigated. So the reference will just follow the temperature profile completely. If you heat it linear, like in this example, the reference will also heat up linear. However, the sample will heat up linear as long as nothing happens in the sample. If you think about that phase transition occurs, like for instance a melting process or a boiling process, then all the heat which is transferred from the furnace to the sample will not be used for further heating of the sample. Instead, it will be used for this phase transition. And that's why the temperature of the sample firstly stays constant during this transition. And after the transition is finished, the sample temperature will relax back to the system temperature, which is nothing else than the furnace. And what the method itself is doing, it is measuring both positions individually, and then we combine them by more or less subtracting each other from itself, and then you obtain this signal, which is a typical DSC curve, where you can look for onset temperature, which are defining the starting of phase transition. We have peaks and set as also important points, and the area of this curve is typically referring to the energy consumed or released during these reactions. With the help of this kind of method, we can also analyze different kind of things. And first of all, again, we can identify, characterize samples or products. Here, we typically characterize the energetic or caloric effects of, for instance, melting reactions, so transitions enthalpies. At the same time, we of course see the temperature where these transitions occurs, like for instance, melting temperature, and therefore can then be combining these things to phase diagrams. At the same time, of course, you can do it also by cooling, so also crystallization is available. We can obtain information about the degree of crystallinity if we think about semi-crystalline structures, and for amorphous structures, of course, we can look at glass transition temperatures. Here, with the DSC, we have one more special thing what we can measure, and we can measure one of the thermophysical properties of a material, the specific heat capacity, so the amount of energy which needs the sample to heat up. And finally, also advanced techniques like oxidation testing, which is shortened OIT, oxidation induction test or time, and of course, again, kinetics. So far, DSC. Just shortly to summarize it up, in the simultaneous thermal analysis, as already mentioned, we combine both techniques. We combine this balanced beam construction in the furnace and this double sensor system of the DSC to one instrument. So we can measure the mass change and the energetics more or less simultaneously. And we do this because we have now the possibility to measure one sample in one measurement in one system. This allows us to get rid of material inhomogeneity if we compare these two effects, because we measure them on the same sample, the same counts for the sample preparation. It is the same sample for TG and DSC analysis, so we have no difference in the sample preparation for both signals. Furthermore, the measurement conditions are the same because both signals are measured in the same system at the same time. And because we measure at the same time, we in principle shorten the measurement time in comparison to a subsequent analysis of TGA and DSC. So far, now you're more or less an expert what is an STA, what is an TGA, and what is a DSC, and therefore we will now head over to the application part. In the application part, as I already mentioned in the introduction, we will have a look here on a general ceramic processing chain, which is more or less consisting of 4 main parts. We will have a look at raw materials, we'll have a look at processing, we'll have a look at product characterization, and some application processes. And as you see here on the right side, each of these steps has different properties which are more or less important for them. So for instance, the raw material, of course, we want to check if it's really the raw material we want to have, so we want to identify it, for instance, or we want to check the composition. For processing, of course, thermal stability over process parameter itself. So how high must I go to really get a reaction or get a melting of some kind of materials in my war mixture, for instance. For the product, of course, thermal properties could be interesting. So specific heat, maybe phase transition, melting temperature, whatever. And finally, for the process application, there's maybe the chance to simulate some application behavior right in front before we use our products. So let's start with the application. I will combine now the two steps of raw material and product characterization because in principle both are counting more or less for the same. You still try to characterize or identify a material. And my first example is covering the raw material here. So we have here mineral material, so just standard carbonate material with dolomite, which is a typical mixture of calcium magnesium carbonate. So here, for instance, we can just heat it up under normal condition, which means normal heating rate 10, maybe 20 Kelvin per minute if you want, and an air atmosphere. What you will get is a decomposition step. Here we see a broad step, first of all, which is in principle give us the information of the carbonate content, because here we see the decarboxylation reaction. This can be directly correlated to the carbonate content of the original material. However, here we see a special part or special measurement because we know in principle that it is a calcium magnesium carbonate. However, if we look at the mass change curve, or especially the DTG curve here on top, which is the mass loss rate, we see 3 steps instead of the expected 2 decomposition steps. And this is because we talk here about equilibrium reactions. So we can influence the reaction, especially the second reaction here, by the released gases of the first reaction. This comes because we use here special lids and everything. So we just mimic that there are 3 steps. This is not good in principle because we want to know really the composition of the calcium magnesium carbonate directly. However, because it is an equilibrium reaction, we can also influence it directly by just changing the atmosphere. So if we're changing the atmosphere, for instance, to carbon dioxide, we can easily influence how the decomposition reaction occur, because the magnesium decomposition is not so much affected by carbon dioxide partial pressure like the calcium carbonate decomposition, and therefore you can now completely separate both steps. Now you see also that it are only 2 steps, and you see the ratio of the magnesium versus the calcium carbonate quite easily. So we see here a good technique to identify, for instance, these typical natural stone material which can be used as carbonate source. Of course, we can go further with these kind of testing. So we can, for instance, also have a look at hydrate water content. Here an example of a calcium sulfate material. And we use here the same principle. And normally, if you just would heat it up on normal system condition, you would get a broad mass loss, which is related to the complete water loss. But in principle, you lose water in 2 steps versus the so-called semi-hydrate. And if we use a special combination with this here, a special lid combination, we can also influence this kind, and then you get the information of the dehydrate versus the semi-hydrate mass loss steps, which allows a defined analysis of the hydrate water content. But you can also look for the oxygen content. So for instance, if you're facing materials like, for instance, titanium dioxide, then you may be aware of the fact that titanium dioxide is not typically, or cannot typically be titanium O2. Normally you would have or face sometimes also so-called oxygen deficit phases, which have less than the 2 oxygen inside of their structure. And this can easily be tested by just heating these kind of materials under oxygen-containing atmosphere. And then you see oxidation steps. And this oxidation steps is directly referring to the deficit of oxygen. So we can see here a 2% deficit of oxygen, and this can be directly related to titanium 1 point something. The next one is phase transition in general. So as I mentioned, we can analyze phase transitions like melting, but also structural phase transition. Here, an example with beryllium oxide, which is a little bit special. But what I want to show here, that we can even analyze these kind of phase transition determination testing at higher temperatures. So here we have a phase transition between the hexagonal and the cubic structure phase of this beryllium oxide, which occurs beyond 2000 degrees C. And we also see during cooling that we have a part of isomers between these two kind of effects. So the cooling, the crystallization of the other phase, or the change back to the hexagonal phase, occurs with a slight delay in comparison to the phase change during heating. And the final example for product or raw material characterization is just for specific heat determination in this case now. So here a more or less standard example of aluminum oxide with comparison of measured data in red and the black data of the literature. So here, just to get a feeling, we can in principle analyze with such an STA specific heat up to 1,500, 1,000. So far to the material characterization itself, let's have a look at processing. So, as talked, we want to talk about parameters. First, just a classic example, especially for the company Netsch, which is sitting in Selb in Germany, which is one of the famous towns for porcelain industries. And here we see the glaze structure. So we heat up a glaze on a material. And what we see is more or less a two-step process. In the first step, we see organic burnouts, dehydroxylation, decarboxylation, which is just coming from the materials inside of this glaze. So you can, for instance, check how your dispersion is built up, if the composition of this dispersion for the glaze is correct. And the more interesting part is the second one here over there, which is referring to the melting of this glaze. So here you can directly correlate temperatures for the firing process to get this glaze sticking to the ceramic or porcelain body material. The second one, which I have with me, is a raw mixture reaction. Maybe not the most common one, but maybe some of you are aware of these lithium manganese oxides, which are typically used also as electrode in batteries. And this kind of spinel phase, how it's called, can be built up by a stoichiometric mixture of lithium carbonate and magnesium oxide. What you will see if you heat this up, we get a poured mass loss step in the beginning, which is more or less a double step, and a mass loss at the higher temperatures. So, and if we now looking a little bit more into detail, we will see that we have a lithium carbonate decomposition to the lithium oxide in principle, and we have this lithium oxide which will react with a manganese oxide to form our target phase, the spinel, and this occurs here in the starting part. However, if we go into higher temperature, the structure will already decompose by releasing oxygen. This is what we see here in the last part. So in principle, we see quite easy that between more or less 650 to 750, maybe 800, we have a phase where we have more or less a stable mass. This means this is a perfect area for producing this kind of material out of this raw mixture. Just an easy test, but we can do much more because we can now take this measurement and just changing some parameters. For instance, this measurement was performed under air atmosphere, so oxygen-containing atmosphere. If we change it to inert condition like a nitrogen-containing atmosphere, we will influence the curve. The beginning of the curve is only slightly influenced in comparison to here. But mathematically, if we look here at the decomposition step of our spinel phase, it is shifted to lower temperatures. So here the decomposition already starts at about 650 in comparison here 750, 800. So we see with a not so high partial pressure of oxygen, or more or less a not present partial pressure of oxygen, we will dramatically influence the stability of our phase, and we must adjust the parameters for production. Same counts if we change the mixture. If we change the mixture, especially the lithium carbonate to lithium hydroxide, it will also influence our reaction path. So here we see an early decomposition step, which is referring to the dehydroxylation of this hydroxide. Then we have a second mass loss step, which is more or less related to the buildup of our spinel phase. However, this is not the perfect phase because we see here a mass increase directly after the mass loss step. And this mass increase is referring to an oxidation of this spinel because we built up here a deficit structure because we cannot build a real stoichiometric composition of lithium hydroxide to magnesium oxide for the spinel phase. And finally, the decomposition. So here we see, with just changing some parameters, we have got a broad overview about how this warm mixture is reacting. Next example for processing is a binder burnout process. So here it would be interesting how the sample in principle behaves, how the mass is released. But more dramatically, here we have a special thing which we can apply because we have the possibility to look into kinetics of reactions. Therefore, we want to look into the time evolution of decomposition reactions. This cannot be done with just one heating because you heat it up and you see, okay, it behaves like this, for instance, with a 10 Kelvin per minute measurement like a blue curve. To really get an insight into the kinetic of a reaction, we have to do several analysis of the same material with different heating rates, because then you can see how the curves are shifting, how the reactions are maybe changing. And we have a special software option, it's called Kinetic Neo, which allows us to model these kind of behaviors with physical and chemical reaction models, like for instance diffusion models, 3-dimensional, 2-dimensional, 1-dimensional, or just normal chemical reactions. And at the end, if you can describe your curve quite good, you have a possibility to use these models to predict. And this is the main point. We can now go with our models that are obtained to predict, for instance, mass behaviors or temperature profiles. So for instance, on the mass behavior side, you can give the software your normal temperature profile you run in your production lane, and you see directly how, in principle, this sample should behave without testing. Even if you have a production process which takes several hours, you can test it with a short click and a button to see how your sample is behaving. And if you change something in the process parameter, you will directly change how the sample should, in principle, behave. So you can here compare several kinds of temperature profiles before you really test them. And only the promising ones will be really tested in the long-term measurement. On the other side, you could also let prediction of temperature profiles which are related to special mass loss behavior. Here, just quite easy one, a linear mass loss, and you see here how the temperature profile should be to obtain this linear mass loss. So with the help of kinetic modeling, we are more or less able to even perform comparison of complex temperature profiles without spending several hours or days testing. Of course, at the end, there must be one test, but this is just to get an overview at the beginning, which is quite helpful, I think. Let's come to the last part, which is the application process, so maybe simulation of some application behavior. And here I have one example with me, which is the thermal reduction of cerium oxide. So maybe if you're working with oxide materials, you know that in principle this oxide, or especially the oxide content, can be manipulated by temperatures, so by thermal reduction. What you see here, just as an information picture, we have here a defined oxygen level in principle of about 100 ppm, which was measured with a special oxygen analyzer from the company Xerox. And then we just heat up the sample step-like processes, and you see each temperature step is related to a certain mass loss. For instance, going from 800 to 1300, we see a mass loss of 0.1%. So we build up an oxygen deficit of 0.1% on the cerium oxide. If we're going even further, we have a deficit of 0.3 in addition to the 0.1, so a total of 0.4. What we also see is during cooling, we can rebuild, we can reoxidize. Of course, if we would hold it longer, not going directly down here, we could maybe even regenerate the material completely. So this is just interesting thing. You can directly test if in your application the material is still the one you expect to be, or did it have changed. Here in this opinion, for instance, if you would apply the cerium oxide at 1500 degrees C, you must face the point that you have an oxygen deficit cerium oxide inside of your application. The next example, and this will also be the last one now, is a quite easy, maybe a little bit boring one, but here we talk about cellulites, which is also one of the interesting or common ceramic materials, and they are known for their absorption possibility for water. This can also be tested in our machines. As I mentioned before in the beginning, we are also able to introduce water-containing atmospheres. So we can just introduce wet gas and dry gas in cycles to test, first of all, the capacity of absorption process itself. at a certain parameter setting. And of course, you can look at cycle stabilities of these kind of materials. This can be done not only with water, you can also think about different kind of other gas types or temperature cycles. So we also talk about, for instance, as calcium oxide, calcium hydroxide cycles, and so on. So there are many possibilities just to get a feeling that this is in principle possible also with these kind of techniques. With this, I'm now at the end. Just let me shortly summarize what we have talked about. Just the basic of thermal analysis. We have heard something about TGA and DSC analysis, what we can measure in principle with these kind of materials, and why we combine them inside of or in the STA, the simultaneous thermal analysis. And of course, we have talked about application possibilities for this kind of techniques for the raw material here shown with the dolomite, for processing chain like the kinetic analysis or the cycling tests of the cellulite. With these, I'm now at the end. I thank you for your attention to this webinar, and we will now head over to question-answer part. So you can write questions inside of the software, which I try to answer in maybe the next 10 to 15 minutes if we have enough questions. If you get some questions afterwards, after this webinar, so in 1-2 hours, you have still the possibility to send us the question by email to here ngp_webinar@netsch.com. And if you are interested in general further information of thermal analysis, you can have a look at our homepage, netsch-thermalanalysis.com. And for the kinetics especially, we have also kinetics.netsch.com. So let's have a look. Maybe we have find some questions already. Yeah, at least one question we have. You haven't talked much about the material characterization in principle. What are the possibilities of the main factors which STA could analyze in detail? So the STA in principle, as mentioned, was a combination of DSC and TGA analysis. So in principle, the STA can analyze anything what the individual methods can do. So if we're going back, for instance, we can do all the things which I mentioned before for the separated measurement. So for instance, if we take the DSC, the STA can also do the melting points. If you remember, I have shown the example for the phase transition of beryllium oxide. So in principle, melting is nothing else than a phase transition. So we can, of course, see melting points up to 2400 degrees C with special furnace upsets. We can also look for melting enthalpy, so the energy which is needed to get these kind of processing done. We can have information from the specific heat capacity. So STA can measure the specific heat dip capacity in the same way, more or less, like a normal standalone DSC instrument. And of course, kinetic analysis. The same counts for the TGA. So I think you have seen it in most examples that we can look at the mass change, at the decomposition behavior, at the thermal stability. So this counts all also for the STA. The STA is just the combination of these two kinds of techniques. I hope this answers this question. Let's see what we have more. Okay, here's a question. What is the normal temperature range which could be covered by this STA analysis? We have seen measurements up to 1600, 500 degrees C, up to 2000. So what is the maximum minimum range of this technique? Okay, so the STA in principle is a special instrument design in our case, in our company design. So we have different furnace options on this machine, and these furnace options are ranging from about -150 degrees C up to 2400 if a whole temperature range is being phased. Of course, there is no furnace which can handle these in one step, but in principle there are existing combinations. You can even attach two furnaces at the same instrument, so you can switch between the measurement of the furnaces. So you can, for instance, apply a machine with a furnace going from -150 to 1000 degrees C, and a second furnace going from room temperature up to 2000 degrees C. So an instrument itself could measure a broad range from the temperature point. And there are also special furnaces, for instance, for this water application, where you can really go in with, for instance, with steam, with pure steam. So we have special assistance heater to prevent condensation. And these techniques can, for instance, with steam be applied up to 1200 degrees C. So this is quite special, the temperature range. So here it would be interesting to know your real application. So get in contact with us, for instance. We're going back to our email here, just write your application more in detail, please, and then we can see what is maybe the best solution on furnaces, and so we can really decide how we could achieve your temperature range that you need and with the best point on your application. Okay, so maybe we have here one last question. Let's have a look. Okay, a question to the Kinetic. You have shown this Kinetic example. How could it be used on other kind of reactions? So unfortunately, it did not mention here what kind of other kind of reaction is mentioned. So as described before, we will, in principle, can analyze any kind of decomposition reaction because we try to model the behavior which we are measuring. So if you are, for instance, facing a multi-step reaction like you see here, you can change each of these steps in between to really get the modeling done. And therefore, even complex decomposition reactions or even oxidation reaction, not only decomposition, also oxidation reaction, can be analyzed or can be tried to be modeled with the help of this Kinetic software, with this Kinetic modeling. And then if the modeling fits, you can use it for prediction. So we are not really blocked by a certain kind of reaction type or application type. So we are not blocked to this binder burnout process. You're more or less only blocked if you can model the reaction or can model the reaction. If you can model the reaction with, for instance, diffusion reactions or solid state reactions or just gas diffusion or solid state diffusion, 3-dimensional, 2-dimensional, 1-dimensional, and what else were existing in the field of kinetics. With the help of these kind of technique, we can model the process, we can use these kind for the prediction examples I showed you. So here's really the point. If you are interested in the kinetics, please have a look here on our homepage with kinetics.net.com. There are really many examples and also a detailed explanation how this technique is working and what you can do with it. With this, I'm now more or less at the end. We have no further questions open. As I mentioned before, you get the possibility to also submit questions afterwards. Just write us an email with netch_webinar@netch.com, and then we will try to help you further. Oh, I see there are coming some new questions. Unfortunately, I can't. Okay, there's one more. What is the difference between DTA and DSC? So this is just a point of how you will look on the detailed here. Wait a second. So how you look on the sensor itself. So if we have a plate-like sensor with a good thermal contact, we have here DSC. So DSC from the standard are so-called two types of techniques. One is a power compensating, where you have separated furnaces for each type of technique, which are not being possible with STA more or less, and the so-called heat transfer, heat flux technique. So you need a thermal bridge, a thermal connection between each side, and this is here achieved by the sensor construction. So this shaped like design here builds a thermal bridge, and therefore you get a heat flux DSC, which has a better sensitivity, a more stable baseline, and a lower time resist constant. So you can also separate small effects from each other. And the DTA didn't have this bridge, so we have two more or less decoupled temperature sensors where you just measure the temperature difference. So we are more or less comparable to this one. So you have no connection here, first of all, and then you get more or less not so stable baseline maybe. There's not so sensitive. So this is more or less the difference of the DSC. So DSC is really a heat flux technique, while the DTA is just measuring the temperature difference, so the difference in thermal voltage. Here I would just give you a point. Unfortunately, I have no slide with me to have a look on our homepage, because there's a detailed explanation for the difference of DTA and DSC, where we have also some pictures where you can see really what it is. So we have one more, I see. Thank you. Do you have any consideration for materials which react with DTA standard material at temperatures? Example, lead oxide with aluminium standard. Of course, this is in principle one of the general questions on ceramic materials. So we need to talk, especially in the high temperature field, about material interaction. So normal materials for crucibles, so to put your sample inside of the machine, are typically aluminium oxide or platinum materials. So for instance, maybe I have one example with me, I think so. For instance, this beryllium oxide is measured in tungsten. No, unfortunately, I don't think so. Okay, so here the point would be that you must face what type of different materials are available. So for lead oxide, I will not go with aluminium oxide. Of course, it will react, it will form a ternary phase, which is not, of course, a problematic point. So you need to find a material which will not react with them. So typically, you could go for more stable oxides, maybe, which would be yttria, also yttria oxide. There would also be the possibility to go to other types of ceramics like bornitride or magnesium oxide or cerium oxide. Unfortunately, I'm not completely sure right now what will react with lead oxide. So we must have a look. I will cover this and then maybe send you an email afterwards. There's also still the possibility to go to metallic crucibles, so typically platinum crucibles. Here's the question: if we have just pure lead oxide, most likely it will work with the platinum up to a certain point without any problem. But then maybe thermal reduction of this platinum lead oxide could lead also to reaction with the platinum, but I'm not completely sure at which temperature you will face this problem here. So here we must look at detail, so we will send you afterwards a more detailed answer, if this is okay. So next, more questions. How many milligram can you put for the best STA measurement? So this is an interesting question from the application side. In principle, you need a mass of sample to achieve the position you want to have. For instance, if we take this measurement, which is right now open here, if you want to achieve a significant mass change in 0.1%, you should think about what is the standard derivation of your machine, which can be easily measured by just making some blank ones, so empty crucible ones. And when you see how 3 empty crucible ones are differing to each other, for instance, if we say it's 10 micrograms, then if you want to achieve the 0.1%, you just multiply it with this 10 micrograms of significance or accuracy of your machine, and then you directly know what is in principle the necessary sample mass to achieve at least the precision on the TG curve you want to have. For the DSC, it's a little bit more complicated. You just start normally with the TG mass loss step, get this sample mass, and look at the DSC signal. If they are not strong enough, not perfectly separated down, you can adjust the sample mass. For instance, if they are too small, you normally go with a higher sample mass. If they are overlapping, maybe a smaller sample mass can separate them better. So this is really depending. In principle, if we go to our machines, you have a wide field of sample masses, sorry. And the sample masses range from more or less 0, of course, and up to several grams, up to 35 grams if you really need it on special machines. So here you just need to adjust what you want to see. So for instance, if you have impurities in 0.0 something range, you can go with grams, 5 grams for instance. So this is really depending on what application you want to have. So with these questions, we are now at the end, really. Again, thank you for your attention. Even thank you for the attention staying through the whole question and answer section, even if they are not your questions. And just let me mention again, if you get further questions after the webinar, please contact us under the here shown email address ngp_webinar@netsch.com, and we will try to find answers for your question. Thank you so far. I hope you enjoyed it. Goodbye.